All right, so now let's ask how we can use Hardy-Weinberg to predict the genotype frequencies in the next generation. So let's think about our initial generation, which we'll call T0. And let's think about some genotype frequencies. So the frequency of the big A allele here is 0.64. The frequency of the heterozygote, big A, little a, is 0.32. And the frequency of the little a genotype is 0.04. And so we have our genotype frequencies. We can now compute the allele frequencies using the relationship that we learned. And so let's ask, what are the allele frequencies? And of course, the allele frequency of the big A allele is equal to the frequency of the big A homozygote plus half the frequency of the heterozygotes, which in this case is 0.64 plus half of 0.32, which is equal to 0.8, and that is our P. Now, of course, we know what Q must be, but let's go through the process to make sure that our mathematics is right here. So the frequency of the little a allele is equal to the frequency of the little a homozygote plus half the heterozygote frequency. That is 0.04 plus half of 0.32. And of course, that is equal to 0.2, which is our Q. And so P plus Q equals 1, and everything is good. Okay, so we have our current genotype frequencies. We can calculate the allele frequencies in the current generation. And what we'd like to ask is, what are the genotype frequencies going to be in the subsequent generation? Okay, and so to do that, of course, we can use Hardy-Weinberg's law up here. And so let's compute that for the subsequent generation. So let's just take our P over here is 0.8, Q is equal to 0.2, and let me just erase this calculation here, because now what we are interested in is what are the expected genotype frequencies in T1, in the next generation, given that these are the current allele frequencies. And so here's where we can use Hardy-Weinberg's law to be able to compute these values. So the frequency, the expected frequency of the big A genotype is simply going to be our P squared. And so that is 0.8 squared, which is equal to 0.64. The frequency of the little a is simply going to be Q squared from here in Hardy-Weinberg's law, which is equal to 0.2 squared, which equals 0.04. And then our heterozygotes, big A, little a, are going to occur with this frequency 2pq, which is 2 times 0.8 times 0.2, which equals 0.32. So here is T1. All right, so we started with these genotype frequencies in our existing generation, which we call T0. We have these frequencies of each of the 3 different genotypes. We use that to compute the allele frequencies. And now we've used Hardy-Weinberg's law to compute what is the expected genotype frequencies in the subsequent generation, the next generation. And what we see is that in the next generation, the frequency of the big A homozygote is 0.64, which is actually exactly what it was in the initial generation. The frequency of the little a homozygote is 0.04, which is exactly what it was in the current generation. And the heterozygote, big A, little a, is 0.32, which is exactly what it was in the current generation. And why is this the case? Because this population is literally in equilibrium. And so this is what we define Hardy-Weinberg equilibrium as being is when the population is literally in equilibrium, such as we observe with this population now. And so this was a really important finding when, even though the mathematics is, incredibly trivial, and in fact, these were mathematicians who discovered this principle and thought it was so trivial that it took them a long time to publish this finding. But the important implication here is that genetic variation is neither created nor destroyed by the process of transmitting from one generation to the next. And so the population, the genotype frequencies remain stable in a population that is in Hardy-Weinberg equilibrium. And so just to convince yourself of that, I'd like you now to just work through the calculation and tell me what the genotype frequencies are going to be in the second generation, given that these are the genotype frequencies in the first generation, following the one that we are currently studying.